All right, so what I want to do today is introduce to you what I call semi-quantitative thinking or semi-quantitative derivation. And the point of this is that physics is hard. Solving physics problems is hard. But sometimes you want to be able to think clearly and intuitively and quickly. And you don't want to have to solve some like annoying differential equation every time you want to know the answer to something, at least roughly. So like, let's start with the harmonic oscillator, right? What's the famous result for the energy of a harmonic oscillator? Okay, its energy eigenspectrum is E of n is h omega n plus 1/2. So suppose you're doing an experiment, right? Like you're in the lab setting up your apparatus or whatever, and you know that you're going to have some kind of harmonic oscillator in your experiment and you want to understand it. But you need to know something really basic, like I'm going to make a confined state with some size. What's that size going to be? Is it going to be like a nanometer? Is it going to be like a millimeter? You know, is it going to be a meter? I need to understand basically how big it's going to be. And I know it's going to have some minimum energy. How big is that energy going to be, and what's its energy level space going to be? Okay, if you want to understand the answers to those questions in a mostly correct way, and you want to do it quickly, like at the level of the back of a napkin while you're talking over dinner, how can you do that? Right? You don't have time to go, solve a differential equation. You don't have time to futz around with the algebra, creation, annihilation operators. You just want to do it quickly so you can understand things, right? Like physics research proceeds at two levels. First, understanding things quickly, and then once you basically know the answer, doing things precisely, right? That's how we kind of all do stuff. That's how we think of problems. Otherwise, it would be too hard to even think of a problem or expect what the answer is going to be or whether it's going to be interesting. Okay. So the skill that sort of everybody acquires at the level of being a professional physicist in the business for a long time is what I call semi-quantitative thinking, and no one ever teaches it to you explicitly, so I'm going to try to teach it. Okay. And the key recipe for semi-quantitative thinking is that you stop using the equal sign and use a squiggle sign. Okay. What does this mean? A squiggle B, okay, means A is equal to B times some number of order 1 that I don't care about. Okay, so let's try this out, right? Someone tell me what's the volume of a sphere? Volume of a sphere. Someone just, okay, put an equal sign, so give me the right answer. 4/3 pi. 4/3 pi r cubed. Okay, what if I had written a squiggle sign instead? What's the volume of a sphere? R cubed. Okay, great. How about if I have a cylinder of, how if I have a cylinder of size, diameter L and height L, what's its volume? L cubed. It's also L cubed, right? Okay. Well, how about if I have a pyramid, like the Great Pyramid, in Giza, and I say its height is L, and this angle is, I don't know, 45 degrees or whatever it is. Okay, what's the volume of the pyramid? L cubed. Okay. So when you do semi-quantitative reasoning, you allow yourself to not care about factors of 2 and factors of pi and factors of square root of 2 and whatever. Okay? And that seems like a small thing, but I'll see in a second that it liberates you and allows you the answers very quickly. Okay? It allows you to stop doing integrals, it allows you to stop taking derivatives to a great extent, and allows you to very quickly get to answers, and you'll see why in a second. Okay, a lot of intuition goes behind this as well. You have to know a lot of physics to do this sort of thing, but you don't have to do a lot of math, and you don't have to do a lot of calculations. Okay. All right, so let's give it a try. Let's think about the harmonic oscillator. Let's start with what is the size and energy of the ground state going to start by drawing like a real cartoon picture. Okay, so here's my confining potential. You know, u of x is 1/2 m omega squared x squared. I'll tell you, would you rather use k or do you want to use m omega squared? Is either one okay with you? Let's use m omega squared, right? If you want to think of it as kx squared like a spring, that's fine too. Okay, so the first thing you do when you're doing semi-quantitative reasoning is you free yourself to stop writing the 1/2. Okay, so that's like m omega squared x squared. Everything that has units you have to keep. But everything that's just a number of order 1, you stop writing. Okay, that's the first thing. Now we're going to imagine a wave function. So here's the wave function. Sorry, this is the physical coordinate I'm drawing here, right? X. Okay, and then you say I drew some kind of lump. Then I call the wave function psi. And now you can immediately say, wait, what is that lump? Is it Gaussian? Is it a polynomial? Is it whatever I say? Don't ask them dumb questions. It's a lump. And what size does it have? Let's give it a size. Its size is r. Okay, this is the size r. And you say, wait, what do you mean by r? You mean the expectation of the position value squared or whatever I say? Don't ask dumb questions. Just the size. Okay. And if I'm freeing myself to not make it precise to within factors of 2 and pi, I just say whatever it does in size. Okay. Very good. Now, what is the potential energy? So this is the ground state. Psi 0. All right. Let's remind ourselves, if this is psi of x, what would it look like in momentum space psi of p? If I make a lump that has some size r in position space, what would the wave function look like in momentum space? Roughly speaking. Some other kind of lump, right? Centered around 0. Some other lump. Okay. What's the size of this lump in momentum space?
H bar over r.
H over r, very good. So it's got some size. I don't know, let's call it delta p, if you want. Okay. So, and delta p is h over r by the uncertainty principle. Okay, that's like the first idea of quantum mechanics, is that if something occupies a range of space, it occupies a range of momentum. Very good. All with me so far? All right, so what's the kinetic energy of this harmonic oscillator? Well, let's start with potential energy. Let's do potential energy. What's the potential energy of this harmonic oscillator state? Now you're thinking, okay, I gotta write the potential energy operator, which is 1/2 h omega squared, and I have to take its expectation value. And then I say, no, you're doing things the hard way. Just look at the picture and tell me what's the potential energy of this thing.
M omega squared r.
M omega squared r squared. And then you want to say, wait, it doesn't have one position r, it has a range of position. I say, I know you're doing an integral, whatever. But like its typical deviation away from the origin is r. And so its typical potential energy is going to be m omega squared r squared. With me. Okay. Now, how about the kinetic energy? What's the kinetic energy going to be?
Minus potential energy.
That's true, but that's not helpful yet because we don't know what the energy is. We don't know what the total energy is.
H bar squared above m r squared.
Okay, yes, so let's just look at this delta p, right? So it's something like delta p squared over m. And then you say, wait, isn't kinetic energy p squared over 2m? And I slap you for writing a factor of 2 when you're not good enough. We're not doing something good enough for factors of 2. But I say this thing has a range of momenta simultaneously, but the typical magnitude of momenta is like delta p. Okay? So the kinetic energy is like p squared over m, which like, sorry, remind me your name?
Me?
Yes.
Schwann?
Sorry?
Schwann?
Schwann.
Yeah.
Okay. Like Schwann said, this is something like h squared over m r squared. Okay. This h squared over m r squared you should start to feel real familiar with. It gets called quantum confinement energy. Anytime you confine a particle to some range of position r, it's going to end up with a kinetic energy of order h squared over m r squared. Very good. Okay. Now, what do? So we say if the wave function has some size r, it's going to have potential energy m omega squared r squared. If it has, and immediately that means that it's going to have a kinetic energy h squared over mr squared. Very good. So now, how do we figure out which size r, we haven't said what r is, how do we figure out which size r the wave function wants to have?
Minimum energy.
Some of you are not used to ascribing intention and will to wave functions, but we're going to start doing that. Okay? Yeah.
If we experimentalists and say, like, we look at an energy transition to figure out what that is.
Okay, good. So we're trying to, this is before we do the experiment. We're setting up the lab, and we're like, oh crap, I need to set up my apparatus, and like, I need to tune to some frequency. Which frequency should I be looking for? And I need to trap it in a potential of some size, and what size am I looking for? You know, you want to know basically like, what, you know, when you try to detect the transition, am I going to use radio waves, am I going to use microwaves, am I going to use X-rays, whatever. You want to know basic things about it. So before we do the experiment, we need to know something. So you're right, in the end, we will learn the energy by looking at transitions experimentally, but I need to know, like, generally speaking, what am I looking for? Okay. But what we figured out here is that if I have a wave function of size r, its potential energy is m omega squared r squared, its kinetic energy is h squared over mr squared. And so now r is something that we don't know, and now the question is, which r is the wave function going to choose?
Minimum total.
Minimize the total energy, okay? So I'm going to say the ground state has r that minimizes potential energy plus kinetic energy. And that means the derivative with respect to r of m omega squared r squared plus h squared over m r squared is 0. Okay. If you were to write this thing, the potential energy is growing with r as r gets big, and this thing is falling with r and blowing up when r gets small, and so there's some minimum at some finite r. Okay. Good. So what's the derivative? What's the derivative of m omega squared r squared?
2m omega squared.
Okay, good. Come up here so I can slap your hand for saying the number 2. M omega squared r. Okay, good. What's the derivative of this thing?
Minus h squared mr cubed.
Yeah, good. You learned this time. Minus h squared over mr cubed. Okay, sorry. I guess I no longer get to write an equal sign. I have to write a squiggle now. Okay, squiggle means I'm dropping all the factors of 2 and stuff. Okay, so let's just solve it. R to the 4th is h squared over m squared omega squared, which means r is, okay, again, sorry. Eventually I stop writing squiggles and just know that equal sign means squiggle, but you guys are young, I won't do that to you. Okay, h over m omega. So now, by this kind of Mickey Mouse logic, we've immediately figured out that, oh, the right order of magnitude for the size of the ground state is h over m omega. Okay? And this turns out to be, I think, by chance exactly correct. I think that we don't, if you do the real answer of like root mean square of the ground state, I think it's exactly this, and there's not even a factor 2 missing. Maybe there's a square root missing out. Okay. So good, so now you can say, oh, okay, I look at that and I can tell immediately whether the size of this thing is going to be nanometers or angstroms or whatever. And I just have to keep in mind that I might be off by a factor of 2 or something. But now at least I know how to set up my experiment. Yeah.
I didn't really get how we found the kinetic energy.
Okay. So the wave function has a range of momenta simultaneously, right? It's peaked at 0, but typically deviating away from 0 by some amount delta p. If you wanted to calculate the kinetic energy, you would integrate psi of p mod squared times p squared over 2m, right? You would say it has weight at different momenta. Okay? The weight part, and each of those momenta has a corresponding kinetic energy. The mod square of this wave function sort of tells you the probability density at different momenta. Okay? So if you were to integrate that probability density times p squared over 2m, you would get some kinetic energy. But you can sort of look at it and say, well, the typical magnitude of that momenta is delta p. Okay? You can plus or minus, but the typical momentum that it has, if you think about it semi-classically, it's just like jostling around inside this potential well. At any given snapshot in time, it has a typical momentum delta P, which is h over r. Okay. So then I can say, okay, the kinetic energy is P squared over m. Which P should I use? Well, use its typical momentum. Okay. That's the kind of thinking we're doing.
Another.
Yeah, go ahead.
Okay, so we know the energy. So we know that's going to be in ground state, right?
Yeah. We sort of,
we don't know what's the
where
ground
we
state.
assumed the ground state is here when we said we're minimizing the total energy. So we're trying to find the ground state.
So we know that it's going to be in ground state and it's going to be fault path.
Yes.
Sure.
Yeah.
So isn't the case that like if it's a ground state, it is like a single energy, so the momentum can only go like momentum can only have two values. It's like P minus P.
Okay, maybe you're thinking about like a square well or something,
Uh-huh.
where you have a superposition of plus P and minus P.
Yeah.
In a harmonic oscillator, okay, by chance, the ground state of a harmonic oscillator is a Gaussian in real space. It's a Gaussian momentum space. So it is very much like a lump with some typical magnitude.
Yeah.
We could have done the same thing for a square well, and just say, okay, there's some typical magnitude of momentum, and we get the same answer. We can do that in a second if you really want to. And then if you, like, for a square well, you're right, that psi of P looks like a delta function over here and a delta function over here. But it still has a typical magnitude of momentum that is h over r, where r is the size of the thing being confined. Like this relation right here is just extremely generic.
No, it's
Right.
just like my physics intuition is clashing with my Fourier transform intuition. Just like
Yeah, I mean,
psi x, if I take the Fourier transform of a Gaussian, it's going to be Gaussian, but I know that P should be like, the momentum should be plus P or minus P. So it's not a Gaussian. Just like two.
Wait. The Fourier transform of Gaussian is a Gaussian, right?
Yeah,
So I really am drawing an accurate picture that it's a lump in real space, it's a lump in momentum.
I know, but my physics intuition says like it should be plus P or minus P.
Okay, all right, well,
It's not like that.
and we're building a new intuition for you. That's what we're doing right now, okay? You're not going to be shocked by the answer, although I have fun things in mind to show you. All right, very good. So now we've arrived at, this is the basic size of the harmonic oscillator. How do we get the ground state? Oh, and by the way, minimizing the sum of kinetic and potential energy is basically the same as saying the potential energy is the same order of magnitude as the kinetic energy. Right? Any harmonic oscillator has that. The potential and kinetic energy are same order of magnitude. So you could have immediately just set these equal to each other. Taking the derivative and just setting them equal only differs by some factor of 2, which we're immediately throwing out because we're not good enough for factors of 2. Good. All right, so how do I get the energy now? So the ground state energy I should take this value of r that I got and plug it into something. What should I plug it into? Can't tell if you guys all find this so boring that you don't want to say anything or you're like perplexed. If I plug r into something, what should I plug it into?
The sum.
The sum. Or might as well plug it into either one separately, right? It doesn't matter. I've said that they're the same order of magnitude, so I can plug it into either one. So I can just plug r into whichever one we like better. Let's do this one maybe. Let's say it's m omega squared, and then I have to do h over m omega squared. And surprise, surprise, that's going to be h omega. And now you say, aha, the real answer is h omega over 2, and you just got h omega. And I say, yeah, like, you know, we saved ourselves an enormous amount of math at the cost of just not getting factors of 2 right. But you immediately figured out that, like, okay, this is basically the answer. So we arrived at, like, actually a very important conclusion in quantum mechanics, which is that the ground state energy of a harmonic oscillator is not 0. It has a finite size, it has a finite energy. Okay, and we did it in, like, a very cheap way. Okay, good? Happy? All right. Should we try to get the full energy spectrum? You can get the full energy spectrum if you want. You know, like the other famous thing about the harmonic oscillator is that the energy levels are spaced linearly in, you know, n. Should we try to get that too? Okay, let's do it. So let's get the spectrum. Well, what we have to do now is just not imagine the ground state anymore. We have to imagine an excited state. So here's my confining potential. Okay. If I want to draw a wave function just as like a picture, that's not the ground state. How do you draw it? What does an excited state look like? Just drawing the wave function, what does it look like? Ground state tends to look like a lump. What does an excited state tend to look like? Has bumps in it, right? So it has some bumps in it. Okay. How many bumps does it have in it? Just roughly.
And
It has n bumps, right? So it's again going to have some size r. But the nth excited state has n bumps. Okay, so nth excited state has n bumps. Okay. What's the size of a bump? Size of a bump in the wave function. Okay, that's true. Yeah, it's r over n. How is it related to something about the well? Okay, I'm being obtuse. The size of a bump is the wavelength, right? Okay. So what we have is that r is n lambda. Good. Okay, maybe it should be n lambda over 2, whatever. Don't mess with it. Maybe it's n and maybe it's n half wavelengths, or I don't know. Okay, we're not going to be good enough for that. So now let me write this as 1 over lambda is sorry, I can't do algebra in front of people. N over r. Okay, actually in the notes I was, okay, it's fine. In the notes I kept a factor 2 for some reason. Should slap my hand. Okay, good. What does 1 over lambda relate to? Okay, 1 over lambda is like the kind of the wavelength of this sort of standing wave thing that we're drawing. What does 1 over lambda tell you? Momentum, right? What's the relationship between 1 over lambda and momentum? H over lambda is like P. Okay, that's the typical momentum. Okay, great. Okay, so let's again write the kinetic and potential energy. So sorry, that's P is like H n over r. Okay, so I have an nth excited state, and typical momentum is H n over r. Okay, good. So now the kinetic energy is something like P squared over m, which is H squared n squared over m r squared. Great. How about the potential energy? Potential energy only depends on the typical displacement of the wave function from the origin, and that's r, right? So the potential energy is the same, m omega squared r squared. Okay, good. Okay, so now I can again solve for this thing if I want. I can take the derivative and set it to 0 if I want, or I just remember that potential energy is going to be the same order as kinetic energy. You know, all oscillators have that. They're trading kinetic and potential back and forth with each other. Okay, so I come here and I say H squared n squared over m r squared is of order m omega squared r squared. Okay, or r is, I'm going to get the same thing I got before, but now there's an n in the square root. So good. So now what we're seeing quickly is that as I go to higher and higher excited states, the size of the oscillator gets bigger. Makes sense, right? It's expanding outward in the potential well, but it's growing like square root of n. Okay. So now I can say the total energy, I can plug this R into either kinetic or potential. They're sort of the same. E is H omega n. And there we go. we arrive immediately at the idea that my energy levels are spaced linearly by an amount h omega, and that the spacing is constant between them. All right, so what did we get wrong here? What does this thing get wrong? This n, the way I wrote it, I guess starts at 1 and goes 1, 2, 3, 4, etc. So if you had taken this literally and incorrectly assumed that you're allowed to keep all the numerical coefficients, you would have said the energy levels are h omega, 2 h omega, 3 h omega, 4 h omega, when in reality they're 1 half, 1 and a half, 2 and a half, 3 and a half, etc. But that's not bad for this level of math that didn't involve any integrals or wave functions or operators or anything. Okay. So anyway, this feels a little dumb. You're like, this is something I already knew, and you derived it in a way that I don't trust. But I want to show you that this kind of thinking gets you answers very quickly. And then once you know basically what the answer is going to be, then you go and do the real calculation, and you can check it all along the way with intuition that you have. Yeah?
Question: why does n excited state have n box? Why?
Okay, so what I'm doing is I'm really using intuition from like standing waves. You know that a wave function, an eigenstate wave function, is a kind of a standing wave. And maybe you learned in quantum mechanics that the number of nodes in your wave function is proportional to the value of the excited state or something, at least in one dimension. So this is just kind of me importing intuition from standing waves. Okay, I sort of know that the higher the frequency, the more nodes I have in it. It's a little bit of a leap of intuition, but in 1D it's literally true. In 1D it's just literally correct that the nth excited state has n antinodes. That's some theorem, who's that I can't remember. So you remember that theorem from undergrad. Look, doing this kind of thing requires a lot of physics education. You're like, oh yeah, I learned that thing. I don't want to make it seem like you didn't have to learn quantum mechanics.
I don't know if I'm jumping the gun on this, but like you said, this will help us like gauge like an order of magnitude of like where to put our energy, where to measure our energy, where our excitation.
Right.
But like I don't know how to like intuitively guess what R and M are, and M and R are. So like
yeah. So first of all, we figured out what R is.
Yeah, you're given M and omega.
Yeah.
But are you saying I don't know what omega is?
Well, okay. So you have to know what. So M is the mass of the thing you're looking at.
Yeah.
Presumably you know. You look it up. It's a proton. It's an electron. Whatever.
But
M omega squared is a property of the trap you're creating. It's the spring constant of the trap. So you have to know that. You have to know something about what trap you're making. But once you know that, the spring constant and the mass, then you know everything else.
So we don't know what the mass is because we're in a solid state. There's effective.
Okay, yeah. Well, okay. I don't know what your experiment is, but I hope you know what the thing is that you're doing an experiment
So
on.
like I'm thinking like, okay, I know, let's say an exciton has like 1 eV.
Okay. You're getting way ahead. We're gonna get there.
Okay.
I'm imagining like a literal harmonic oscillator. Like you trap your rubidium atom in an optical trap or something, and you know the spring constant because you know the strength of the lasers or whatever, and you know the mass because it's a rubidium atom thing. We're gonna do all sorts of complicated mapping of real things like excitons and photons and polarons and whatever, phonons I bet, onto the harmonic oscillator, but that's the point of the course. All right. Should we use this to do something that's less trivial? Let's do like this. I don't know if this feels to you like I derived an answer that you already knew in an untrustworthy way. So let's maybe use it to derive something you don't know already. Actually, I want to do 2 examples of it. I'll do one, and then you can tell me whether you want the second one. Let's do the quartic oscillator. Haven't I heard this? I think I just called it K again. No, I called it gamma. Okay, for some reason this is the way people always write it. 1/4 gamma x to the 4th. Okay. So this is a confining potential that doesn't have a parabolic term. It's a flatter potential that goes up like x to the 4th. Anyone know the answer to what are the eigenstates of this thing? Anyone seen it in a class before? Okay, you know why you haven't seen it in the class? Because it does not have an exact solution. Like, it seems like a very slight modification, but you just turn that x squared to x to the fourth, and it's just literally unsolvable, as far as we know, by exact methods. You have to do numerically. Okay, but let's just try to get the answer anyway. Let's cheat. And try to get the same answer. So again, what I'm going to do is I'm going to draw the same picture of like some lump of size r and with n nodes in it, n antinodes. And now I say r is n lambda, and h over lambda is p. I still have that. Okay. So I still have hp is h over lambda, which is like hn over r. Okay. So, and I still have the kinetic energy is like h squared n squared over m r squared. You know, I didn't use anything about the confining potential to get to this conclusion. It's still true. Okay, the only thing that's different is that now the potential energy is, what's potential energy now? How is it related to r, the size of the wave function? R is the size of the wave function. I'm being very vague about what size means, but whatever, it's somehow the size. And now I'm in a quartic potential that goes like 1/4 gamma x to the fourth. So what's the typical potential energy? This isn't a trick question, it's just gamma r to the fourth. Because now I don't have a parabolic increase of energy, I have a quartic, so there we go. And I didn't write the 1/4 again because I'm not writing any numbers. Good? Okay. So now I can again, if you want, we can say that kinetic energy is the same order as potential energy. Or if you feel queasy about that, you can do or dpr of kinetic energy plus potential energy is 0. Okay. And what you'll get here is something like h squared n squared over m r squared is of order gamma r4. Okay, let's solve that. R double. I'm kind of skipping lines of algebra just because it's like mind-numbing to watch someone do algebra in front of you. You can check if you want. There we go. Okay, you're going to get a 1/6. Now, plug in this R to either KE or PE, and we're going to get E is of order gamma 1/3 h squared over m 2/3 and 4/3. Okay, with, and by the way, we define it 1, 2, 3, etc. Okay. So we arrive at a couple conclusions. One is that the typical size of the quartic oscillator is now this thing. You can check that it's dimensionally correct if you want. And the energy level spacing is no longer constant in n. As n gets bigger, the energy level spacing gets bigger. Okay, so the higher excited states are farther apart than the low excited states. Okay, you want to know what the real answer is, just like numerically? It turns out we basically got the answer correct. Modulo the fact that this wasn't 1, it was 0.867, and n should have started from 1/2 instead of 1, just like that. But anyway, it's like a very cheap way to figure out basically what's the answer. And when you're trying to think about, like, how do I understand the problem? How do I get intuition for what's going on? How do I predict what the answer should be? This gets you most of the way there. This gets you to the point where, okay, now I just have to do a real calculation so I can, put it in the paper and not look like an idiot. But most of your understanding and your intuition about what's going on can be derived already from this really simple kind of thinking. And that's what I'm generally in this class going to try to do things the correct way and then the cheating way. Because in my mind, you get much more intuition from the cheating way. Okay, yeah.
So we always have this plus 1/2.
Yeah, this you can get this plus 1/2 from like what's called WKB approximation. It turns out the correct boundary condition has a 1/2 in it, and there's some formal thing in here.
Okay.
But it's just much harder for me to wave hands and draw pictures and justify that 1/2. So I want to be more, pedestrian about it.
Is it significant that like, oh, I did this calculation and then I thought that ground state has 0 energy.
No, I didn't think the ground state had 0 energy because I thought that n had to start from 1. That's important.
Okay.
So just like when we did the ground state of the harmonic oscillator, I knew the ground state had to have energy.
Okay.
So here, when n was like the number of antinodes, and there better be at least 1. What's a wave function with 0 antinodes, right? So maybe I should have called this a different thing, but that's it. It's whether the index here has to start from 1 or from 1/2. But I knew the ground state had to have energy, had to have some size. Yeah, if I had thought that the ground state had 0 energy, that would be a qualitative failure. But instead, I just have a quantitative failure. All right, how are you guys feeling about this? You feeling like this is fun? You feeling like I hate this? It's natural to hate something first before you like it. Many such stories. Like I hated the quantum Hall effect for years before I turned out and learned that I loved it. That's normal. Okay, any questions? You want to do something more fun? Okay, so this class is mostly about collective excitations. And I want to talk to you about a collective excitation. Okay, actually, do you want another example of this kind of thinking on something that you maybe haven't thought about before? And we'll learn about it in a quick, cheap way. Yeah, all right. Let's talk about water waves. We're going to talk about waves of all kinds in this class, collective waves. And in quantum mechanics, everything becomes a wave. An electron is a wave, and a phonon is a wave, sound is a wave, and light is a wave, and everything is a wave. But somehow, we never talk about, the wave that you first encountered in infancy, which is water waves. And so no one knows anything about water waves. You guys know anything about water waves? Basically not, right?
There's 2 kinds.
Okay, good. That's something. Okay, so someone had some education, but you probably didn't even learn it in a class. Did you?
We learned in our waves class, I think.
Oh yeah? Okay.
One homework problem on it.
Okay, all right, good. So maybe this won't be surprising for you. But let's do it anyway. Let's talk about water waves. But actually, let me ask us a focused question, which is, how fast do water waves travel? So suppose I have, I'm going to say water, but this is sort of generic for any kind of fluid. Let me not draw the tank here. Bring in a tank in a second. Okay, so I have a wave, it has a wavelength like this. It's like a ripple on the surface of a pond or whatever, and it's traveling, let's say, to the right. Okay. How fast do water waves travel? And let's say, does V increase or decrease lambda? That's a good question. How fast do waves travel? It does depend on the wavelength, and if so, does longer wavelength mean faster waves, or does shorter wavelength mean faster waves? Anyone have a feeling about this? First of all, you have a feeling for roughly how fast water waves travel? I don't know, kind of walking speed. I don't know, I throw a rock in a pond and it moves a meter per second or something like that. Seems about right. How about whether it goes faster or slower? Which one moves faster, long wavelength or short wavelength? Any ideas? Just a feeling. I'm not asking you to do a calculation in your head, just what feels right.
Long.
You feel like long wavelength move faster? Anyone feel the opposite? Okay, a few people feel the opposite. All right, turns out you're both right, and we'll talk about it, okay? So, if you want to know the speed of water waves, or the speed of any wave, all waves travel at the group velocity. V equals d omega dk. Okay, you guys know now k is 2 pi over lambda, that's the wave vector. Okay. So if we want to figure out how fast a wave travels, we should figure out how quickly it oscillates for a given wavelength. Okay, and if we do that, we take the omega dk and we've got the velocity. Hopefully that's not new to anyone. So how do we figure out omega of k? That's the question. Now the correct thing to do is you write a differential equation for some like little volume element at the surface of the wave, and that volume element has different forces acting on it, and has inertia, and you solve that differential equation, you get an answer. Okay? But I'm not trying to make you solve any differential equations, I'm trying to teach you how to get answers without solving differential equations. So we need some way of thinking that will allow us to figure out omega for a given wavelength. Okay. And here's the piece of visualization that I like. So let's imagine a lambda-sized standing wave. Let's imagine let me say it this way. Let's imagine a standing wave in a lambda-sized tank. Okay, the nice thing is that if we want to think about just omega, we don't have to imagine a traveling wave. We can imagine a wave stuck in a tank, not going anywhere. So that'll be kind of convenient. So here I'm going to draw my tank like this. And this will sort of be the equilibrium height of the water, and then I'm going to imagine something with one wavelength like that. All right, so this displacement, delta, this is the sort of amplitude. I'm making a standing wave of size lambda. And I guess, I don't know, just to keep my units nice, I will imagine that the tank extends a distance L into the board. Okay, otherwise I have confusing units where I do things per unit length or whatever. Okay? Okay, good. So now I'm imagining a standing wave in a tank. It's not going anywhere, it's just like oscillating back and forth the way standing waves do. But it has a well-defined frequency and it has a well-defined wavelength, and that'll allow us to get this. All right. So let's start with here. Why does the wave oscillate? Like if I sort of, froze time and arranged the wave in this way, and then released it, it would oscillate. Why does it oscillate? Okay, there are boundary conditions, but if it's oscillating, then something has to be pulling it back toward equilibrium, right? So what pulls it back? Okay, so what are the restoring forces? Let's start here. What are the restoring forces? Okay, there's gravity. What else? Anything else? Surface tension, right? Surface tension is a force that penalizes your fluid having more surface area than it needs to. Okay, and the configuration with minimum surface tension is the one where the surface is just flat. So when I ripple the surface, I have more surface energy, and that energy is going to push it back toward zero. Okay. So maybe if you took your class, you learned that there are indeed two different kinds of water waves that we call gravity waves and capillary waves. Okay. And those two waves differ by which of these restoring forces is dominant. Is gravity the more important one, or is surface tension the more important? Okay, so let's think now about which force is dominant. All right. You probably learned by now that once you get past like second year undergrad, we don't really think about forces anymore, we think about energies, right? Forces are sort of dominant, energies are real. So let's look at the two options. Option number one, gravity. So let's look at how much gravitational potential energy is associated with this configuration, this state of the wave. Okay? So what is the gravitational potential energy? Anyone think they can walk me through that? I just drew a picture. What do you think is the gravitational potential energy? First of all, what do you remember? You remember some formula for gravitational potential energy, right? What's gravitational potential energy? MgH, great. And I'm running these spaced out because we're going to dissect each of these terms. Okay, G is G, it's just a number. What's H? What should I think about as H here?
Yeah.
Sorry? Who said that? Who might have that? Someone said something. Yeah.
I think it's just delta.
Delta, right? Delta, what we've done is we've basically lifted a mass of water from here to here. And how much have we lifted it? We've lifted about delta. Okay, great. So this is delta. Okay, that's how much we've raised some amount of water. Very good. Okay, how about M? What's M? Well, M is like the mass of the thing that we just raised, right? Okay, anyone want to walk me through what's this mass? How would you think about it? What's the mass of that thing?
Delta.
Density times some volume, right? Density times volume. Okay, I'm going to put the capital V, the volume. And this thing is the volume of the lifted amount of water. Okay, how do we figure out the volume? And this is where you go, oh crap, I gotta use calculus for something, like I have to do an integral from here to here, and I have to divide this into little rectangles and whatever. But we're not gonna do that. Who wants to tell me the volume of this thing right here? Okay, delta cubed would be like a little cube of size delta, so that delta cubed would be this thing. So it's not delta cubed. That would be like a little, ripple with size delta in all directions. But that's not what this thing is. This thing is like a little, I don't know, it's like a trough that extends back this way. Okay? So anyone feel like they can, okay? The volume is like one length times another length times another length. So what are the lengths here? Okay, hold on. So someone said one of the lengths, so let's back it up, right? Okay, I'm talking about like this little object right here that now extends backward like this, like, oh my goodness, drawing is hard. Extends backward like this sort of trough-shaped thing, okay? It has 3 dimensions. Someone give me one of the dimensions.
Delta.
Okay, delta is this one, right?
Yeah.
Okay,
Lambda over 2.
okay, lambda over 2. I'm not going to write the 2. I'm going to yell at you for saying 2. Okay, what's third direction is what? L. Okay, so that the volume here is like delta, lambda, L. Great. Very good. So the potential energy, let's just put this all together, is rho delta lambda L G delta. Okay. And let me write that as rho G L delta squared over K. Okay? Because K, the wave vector is like 1 over lambda. 2 pi over lambda, but don't mess with me right now. Okay? Good? nice thing is, this looks like a potential energy that goes like delta squared. You're like, oh, that's good, because we want this thing to look like a harmonic oscillator. And harmonic oscillators have an energy that looks like displacement squared. So delta is the displacement, and even though this is a collective oscillation, it'd still better have potential energy that goes up like delta squared. Good? Great. All right, let's do option 2. Okay, well, just 1 second. Option number 2 will be surface tension. Pretend I have them all. Okay, sorry, there was an objection.
What is L? Like capital L?
L is the length of this tank, and it better drop out of the problem because it's completely imaginary. I'm imagining a tank that's shaped like a, rain gutter or something, and it goes L distances before it. It's completely imaginary and should not matter for the problem. So I'm hoping that L drops out at the end. Actually, I could have gotten rid of L by just making everything per unit length, but it's annoying, so let's not do that. Is that okay? All right. Good. So let's talk about surface tension. Surface tension wants to bring the wave to a completely flat surface, but instead I have this. Surface tension potential energy is like, I'm using gamma for, gamma surface tension. Times delta A. And this is the area of the water surface. Okay, that's the definition of surface tension. It's the proportionality between the change in area and the increase in potential energy. All right. Let's define a sort of a contour length like this, L. Sorry, that's a little confusing the way I drew it, but this L is sort of just describing the contour length of the height of the water. Okay? And so this thing is now gamma L let's just write this as delta L. And delta L means like L minus lambda. So that contour length is lambda when the water's at rest. And when it's in some sort of, oscillating state, the contour length gets longer. That's right. Any confusion about notation? Okay. All right. So if I asked you to calculate delta L, how would you do it? If you were an honest, well-behaved physics student, how might you calculate L? I asked you to calculate the contour length of this surface. What might you do? You guys remember how to calculate the contour length of a curve? Oh, you do that thing that's like the integral of the square root of dx squared plus dy squared, which means you calculate the integral of square root of 1 plus the derivative squared, and you say, okay, maybe it's a sine wave, and you take the square root of a sine wave, derivative of a sine wave and square it and put inside a square root. And you can do that integral, but I'm trying to stop you from doing integral. So anyone want to make some leap of intuition for how we can estimate what that contour length is going to be?
Triangles.
Yeah, good. Let's make triangles. Who said triangles? Okay, I'm going to bring gold stars. You'll get a gold star next time. Okay, so now I'm going to draw a squiggle and say, let's just replace this thing with some triangles that go like this. Okay, and the height is delta. And this length is lambda. Okay, that's a much simpler thing to calculate the length of. And if you do it, what you'll get is that L is something like the square root of lambda squared plus delta squared. Okay, just Pythagorean theorem or something. Okay, we good? We can go through in detail, but whatever. Maybe I even have a 1/2 missing somewhere. I don't care about that either. All right, so if the amplitude is small, which means delta much less than lambda, And any derivation is going to assume that at some point or another, even your sort of, textbook differential equation one, then L is something like lambda plus delta squared over lambda. Okay? And that's a Taylor expansion. Theoretical physics is mostly an exercise in doing Taylor expansions, so here's one of them. Taylor expand this square root, you get that? All right? Okay, so delta L is something like delta squared over lambda. Okay, and let me write that as delta squared K. Good. Any objections? You guys should object more. I like it when you object. Okay. All right, so good. Now what I have, I'll just plug things in. The potential energy is something like gamma L K delta squared. Great, so we've got delta squared again, which is good, which means this thing is again like a harmonic oscillator, something where the potential energy goes up quadratically with the displacement. So now we get to turn our wave into a harmonic oscillator. But let's look at this just for a second. Gravitational potential energy goes like 1 over k. The bigger the wavelength is, which means the smaller k, the more important gravitational potential energy is, just because the volume of this thing gets really big. Surface tension goes like k, which means the bigger k is, or the smaller the wavelength is, the more important this term is. Okay. So, and that's just basically because you make something with really short wavelength, it gets really choppy, and that involves more corrugation of the surface, more surface tension. Okay. So whether the left term is important or the right term is important depends on the wavelength, or in other words, depends on the wave vector k. Okay. So we can't just declare that this one is important or that one isn't important. They have their domains of applicability. So let's just make sort of a line here, k goes to 0. So these are, this is over here is long wavelength, and over here is short wavelength. Okay, and what I know is that somewhere over here, small k, long wavelength, this thing is going to be important. And over here, big K, short wavelength, this one is going to be more important. How do I figure out where to draw the line between which one is more important? So I should put like a little line on the map that'd be like, okay, gravity waves, this is your domain of, ruling. Surface tension waves, this is where you rule. Where should I put the boundary between them? Where they're equal, great. So let's call this is some, what did I call this in my notes? Oh, I didn't give it a name. Okay, whatever. So this is some, let's call it special K like the cereal. Okay. How do I figure out the special K? Okay, I don't know. Okay, K, call it K naught just because I'm uncreative at the moment. We're going to equate the two things to figure out what that value is. So I say potential energy due to gravity at K naught is about the same as the potential energy due to surface tension at K naught. Okay, so now I get rho GL delta squared over K naught is gamma L K naught delta squared. Okay, delta squared cancels, that's great. It would be annoying if whether I had a surface tension wave or a gravity wave depended on depended on the amplitude of the wave. L cancels, that's good because L was fake. And so what I'm going to get that K naught is something like the square root of rho G over gamma. So this is that sets a scale that separates surface tension waves from gravity waves. If k is smaller than that, these are gravity waves. And if k is bigger, these are, actually we don't say surface tension waves, the technical term is capillary waves. Capillary just means surface tension. Okay, very good. So we've actually arrived already at a pretty non-trivial thing, that there are two distinctly different kinds of waves, surface tension waves and gravity waves. And what is the dependence omega k, or in other words, what's the velocity, is going to be different for the two domains. All right, I think I have time to mostly get to the answer. Maybe we'll do a little bit at the end of the next class. So when I asked you that question of like, you know, does bigger wavelength mean slower or faster? The reason it was a trick is because there are two different kinds of waves, and they're going to have different behavior. All right, good. Should we do it? Yeah. Question? Was there a question? No. Okay. Now, we have these expressions for the potential energy. We had this one, and we had this one. But if I want to understand the frequency of a harmonic oscillator, I need potential energy and kinetic energy too. Okay. So I need to understand what's the kinetic energy, and then I can understand my oscillator's trading potential for kinetic. So now we have to think about the kinetic energy. So let me again draw this picture. This is a tank going back into the board some distance L. I have this business right here. Okay. All right. What happens when I imagine this wave oscillating? It's trading potential for kinetic. And so let's say this is the moment of like, you know, maximum amplitude. What's going to happen is that this part of the surface comes down, this part of the surface comes up, and it acquires some velocity, reaches equilibrium, moves through equilibrium. And that involves some kinetic energy. So an important thing to understand about waves is that, like, if you were to look at which part of the water is moving, it's not just the stuff right at the surface, right? The stuff literally at the surface is moving down, and then it's kind of coming down and cycling through and coming up again like that. So the part of the wave that, if I made this standing wave, and I asked which water molecules are moving, well, some volume is moving, not just the stuff literally at the surface. Some volume of water molecules are sloshing around. And that volume is also order lambda. So the stuff that moves is like one wave within one wavelength of the surface. So the smaller the wavelength, the thinner the layer of water that's actually moving. Okay. So what's happening now is there's some like fluid velocity that involves fluid sort of sloshing through the surface like that. And maybe if you had a waves class, you saw a picture like that. There's some like circles of roiling water or whatever, and they're sort of same size as the wavelength. Yeah.
So is here how we like incorporate the water depth into our energy equation?
Okay. Yes. So maybe I'm implicitly assuming. Okay. I'm assuming the tank is deeper than lambda. You'll see in a second that if you imagine a shallow tank, you're going to get a different answer.
Yeah.
Because you're forcing a narrow layer of water to move, and it has to move faster. So you're going to get more kinetic energy if you move up the bottom of the tank. So let's just assume a deep tank. And then what happens is stuff way down here isn't moving, and only stuff within one distance lambda is moving. That's what we're going to assume, okay? So make this tank deeper in your mind if you want. Okay. All right, so there's some fluid velocity. The fluid velocity, EF, should be such that a volume V, which we said over here is delta lambda L, is moved left to right during one oscillation period. So there's some fluid velocity. What sets the fluid velocity? Well, the water has to move from here to here. Okay. And so we can figure out what the fluid velocity is by just saying that the water that's coming down from here has to move through this region and come back up. And the total amount of water moved had better be such to move this volume from here to here. Does that make sense? Okay. So what we can do now is say, let's do VF times, okay, let me imagine, I wish I had another color, I'm gonna bring more color markers. Imagine this little area right here, okay? This is a cross-sectional area going into the board. Let's call this a cross-sectional, sorry, I have color markers. I'll get it next time, don't worry. Yeah, thanks. AC, which is now something like lambda L. Okay. So the water is flowing across this cross-sectional area, left to right, left to right, left to right. Okay. So something like VF times AC times T had better be equal to the volume of that little cap. Okay. So this is the speed of the water moving, the area across which it's moving, the time over which it moves, and then I'm going to get something that has units of the total volume moved. Is this equation okay? Anyone want to yell at me about it? A silent class is a dangerous class. Makes me feel like I could get assassinated at any moment. All right, good. So let's just keep doing. So what I'm going to get now is VF lambda L over omega is delta lambda L. Great. So what does that mean? VF is something like omega delta. So that's the typical fluid velocity. It's moving at omega, where omega is the frequency of oscillation that we're trying to figure out, and is proportional to the amplitude. Okay. Very good. So how do we get the kinetic energy? Okay, what's a general equation for kinetic energy? mv squared. Thank you for not saying 1/2, m. But now the speed here is not the group velocity at the top of the wave. The speed is the fluid velocity. The fluid is what has the kinetic energy. So mvf squared. Okay. And this mass is the mass of moving water, which is something like lambda squared L times rho. Or times 10 is great. Good. So that's the amount that's moving. This is how fast it's moving typically. Okay, so the kinetic energy is something like, let me just multiply it together, rho L delta squared omega squared over k squared. Good. So this is the kinetic energy. So a wave that's oscillating with some amplitude delta and some wave like lambda, 1 over k, has this kinetic energy. And now it can have either this potential energy or this potential energy, depending on whether k is above or below the special k. Okay, good. So we get, okay, now I have an expression for kinetic energy, I have an expression for potential energy. How do I estimate omega associated with a particular value of k? Kinetic energy depends on omega. Okay, we get omega k by setting what equals what? Yeah, potential energy. Okay. Now let me just do the algebra for you. For gravity waves. Let me just solve that thing for you. What you're going to get is omega is something like square root of gk. Okay? If you're really good at algebra, you can set that equal to that in your head and cancel things, and you're going to get that. Okay. What does that mean about the group velocity? What's the group velocity? I erased it, but how do I get the group velocity from here? Yeah, derivative d omega dk, which looks like square root of g over k. Okay. For capillary waves, I'm going to get omega is, okay, let me not write things wrong, make sure. I'm going to get something like square root lambda k cubed over g, okay, which means v, I take the derivative of that, and I get square root of gamma k over rho. Oh, sorry, did I say g? Sorry, what happened? This was supposed to be rho, I'm sorry. Okay, good. So, let's make a sketch now of what we just figured out. Sorry, I'm not showing you all the algebra in the middle, but you can do algebra on your own. Okay, let's make a sketch of what we did. Omega as a function of k. Generally, anytime you plot omega as a function of k, this quantity is called the dispersion relation. And what do we have here? We're going to have something that, oh, I erased my thing. Okay, first of all, let me put back here k0, which was square root of g rho over k. All right, what I have is something that looks like, here, square root of k when k is small, and k to the 3/2 when k is big. Now, I'm going to do something that all of you should learn to do, even if it makes you unhappy, which is I'm not going to plot this in normal linear scale, I'm going to plot it in log scale. The beautiful thing about log scale is that all power laws become straight lines. And straight lines are easier to draw than like complicated curves. So, this thing will look like a straight line with slope 1/2. And this thing will look like a straight line with slope 3/2. Okay. So I'm going to have here, this thing is like square root of gk, and this thing is like square root of gamma k cubed over rho. And there's sort of an inflection point there. All right, now if you were to really do the differential equation or whatever and solve it, and I actually don't even know if you can solve the differential equation in closed form with full terms in it, but if you did numerically or something, then this point right here wouldn't be like a sharp point, it would sort of somehow be rounded out, but whatever. It'd be within a factor of 2 at this point. All right, now one thing you should do when you get to this point and make the plot is that you should check that the equation you have here matches the equation you have here at the point where they're supposed to transition one to another. And if they don't match, you did something wrong along the way, or you missed some physics. So you can do that, you can just plug in k naught here and here, and you find that they match and you feel it. All right, now let's plot v of k. We're almost at the punchline here, I promise. Okay, v of k, here's some k naught. Okay. What does this look like? Let's do log scale again, right? So all power laws are just straight lines. Okay, so just qualitatively, I want to make this plot, what's it going to look like? The velocity. That's what we started by asking. What's the speed of water waves? Yeah, it has a minimum in the middle, right? It looks like this. And this thing is like, again, square root of g over k, and this thing is now increasing with k, square root of lambda k over g. Rho. Keep writing rho instead of g. All right, so what is this saying? This is saying that waves with very long wavelength out here move very fast. Actually, this is a known phenomenon. Like whenever there's an earthquake or something, it sets off these huge long wavelength waves, and they travel super fast, like a kilometer a second. But also waves with very short wavelength, like, I don't know, millimeters wavelength waves or whatever, those also travel very fast. And then there's something right over here that's like the minimum wave speed. And actually, if you drop a rock in a pond or something, it's going to create wavelengths of all kinds. And the long wavelengths will run away quickly, the short wavelengths will run away quickly, and what you see is like the enduring ripple is this thing. You see the slow ones because they stay around for a long time. Okay? And it happens that this thing right here, if you put in the numbers here, it works out to about, okay, let's call this V min. You plug in K naught for either one of those things, and V min is gamma g over rho to the 1/4. So there's a minimum wave speed that it depends on the surface tension, gravity, density of the fluid. And it turns out that in water, V min is something like 20 centimeters per second, which hopefully feels like about what you're used to. You drop a rock in the pond and you see waves moving, and they're moving at something like 20 centimeters per second. And the wavelength corresponding to that minimum speed, what does it feel like it should be? I don't know. Shouldn't be like a kilometer, right? It shouldn't be like a millimeter either. It's like what you see that's left over after a long time. It's about 2 centimeters. So what you think of as a water wave, probably in your head if you're imagining it, is this speed and this wavelength. But that's because that's the minimum. That's what's left after the high wavelength and low wavelength stuff have moved on. Okay, I hope this feels a little powerful to you. Like, solving this problem for real is difficult, and you can go look it up in some engineering textbook, and at some point you're going to resort to just computers. But if you want to understand it, and as physicists, like understand conceptually what's going on and why, you can use this kind of reasoning. I'm going to keep coming back to it. Collective excitations and dispersion relations are going to be a main theme. And I want to get you a sense of how you can understand it the easy way as well as the hard way. Okay, is this fun? Did you like this? It's a complete digression, but like it's too fun not to do.